Hello, in this lecture we will find out the radius of the small circle. In the drawing we have a triangle ABC. Triangle ABC is a right triangle. In addition, we know that line segment side AB of triangle ABC equals to 6 units in its length. Side BC equals to 8 units in its length. Inside this right triangle we have this small circle and also this big semicircle, and our mission is to find out the radius of this small circle. So first of all, we will implement the Pythagoras theorem on this right triangle, triangle ABC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So here by PT is abbreviation for Pythagoras theorem. The hypotenuse in this right triangle ABC is AC. So the square of the hypotenuse is AC squared, and it must be equal to AB squared plus BC squared. Okay, again, according to the Pythagoras theorem, in the right triangle ABC, AC squared equals to AB squared plus BC squared. AC is the missing side, so we will leave it as it is. So AC squared equals to AB squared. AB is 6, therefore AB squared is 6 squared, that is 36, plus BC squared. BC is 8, therefore BC squared is 8 squared, that is 64. So we found out that AC squared equals to 36 plus 64. 36 plus 64 is 100. So AC squared equals to 100. We take a root out of this equation, and finally get that the length of the hypotenuse AC is equals to the square root of 100, that is 10. And the length of the hypotenuse AC is 10 units. So write it down. AC equals to 10 units in its length. We define the point of tendency of tangent AC with this semicircle. This point is point H. We define the center of this small circle. This point is point P. And we define the point of tendency. We define the center of this semicircle. This point is point Q. We define the point of tendency of tangent AB. This tangent AB with this small circle, this point is point N. And we define the point of tendency of tangent AC with this small circle. This point is point K. And we define the touching point of this small circle with this big semicircle. This point is point T. So here we actually can implement rule 2. We have here, if we focus on this common external point A, from this common external point A, we actually have two tangents to this small circle. Tangents AN and tangent AK. And according to rule 2, they are equal to each other. Actually, for this extra point A, we have two tangents to this big semicircle, tangent AB and tangent AH. And according to rule 2, they are equal to each other. That is to say, AB equals to AH. Again, AB equals to AH according to rule 2. But it is given us the question that the length of side AB is 6, so you can write here that AB equals to 6. And for this equation, 6 equals to AB equals to AH. We derive that AH is also equals to 6 units in its length. So this side AH equals to 6 units in its length. AH equals to 6 units in its length. So what is the value of the missing side HC? From the dominant it is very easy to see. It's very easy to see that HC equals to AC minus AH. Again, HC equals to AC minus AH. AC is 10, AH is 6, therefore in total HC equals to 10 minus 6, that is 4. So I write it down. The length of this line segment HC is equals to 4 units in its length. In the next step, we will join points Q and H together by straight line. What is the definition of line segment QH? Line segment QH starts from point Q, that is the center of this semicircle, and ends at point H, that is the point of the semicircle itself. So this is exactly the definition of a radius. Therefore therefore QH is the radius of this big semicircle. We define the radius of this big semicircle as B, therefore QH equals to B according to our definition. And here we can implement rule 1 because we have the radius QB of this big semicircle that is equals to B. The radius QH of this big semicircle is drawn to point H, that is the point of tendency of tangent AC with this big semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AC will be perpendicular to the radius HQ. If AC is perpendicular to HQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So this angle C, it is a common angle that belongs to both triangles. Angle C belongs to the big triangle ABC, of course, but this angle C also belongs to the small right triangle QHC. So we will define the size of this angle C as alpha. And we will focus on this right triangle HQC. In the right triangle HQC, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equals to 180 degrees. That is the sum of the angles in any triangle. So this first missing angle must be equal to 90 degrees minus alpha. Likewise, we will focus on the big right triangle, triangle ABC. The big right triangle, triangle ABC, this angle equals to alpha. This is actually a right angle. It is equal to 90 degrees in size. So this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha, according to the same rule that the sum of the angles in any triangle is equal to 180 degrees. So as is known, this missing angle must be equal to 90 degrees minus alpha. In the next step, we will prove that the right big triangle, triangle ABC, is similar to this right small triangle, triangle QHC. So I write it down. So the right big triangle ABC is similar to the right small triangle, triangle HQC. So why the big right triangle ABC is similar to this right triangle, small right triangle HQC? First of all, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So here, this is angle ABC in the right big triangle ABC. And it is equal to this angle, that's actually angle QHC. In the right small triangle QHC. So repeat again. Angle ABC in the big right triangle ABC equals to angle QHC in the small right triangle HQC. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both angles, so we can write down that angle alpha equals to itself as a common angle that belongs to both angles. So if we relate to angle alpha as it belongs to the big right triangle ABC, it will be defined as angle ACB, and angle alpha equals to itself. So if we relate to angle alpha as it belongs to this small right triangle HQC, it will be defined as angle HCQ. Repeat again. This equation means that angle alpha equals to itself. We just call to angle alpha two different names. So angle alpha equals to itself. It's a common angle that belongs to both angles. And finally, those two angles, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually, this is angle BAC in the right triangle ABC. And it is equals to this angle, that is actually angle HQC. in the right triangle HCQ. So repeat again. Actually, found out that angle BAC in the right big triangle ABC equals to angle HQC in the right small triangle HCQ. They are both equal to 90 degrees one circle, therefore they are equal to each other. So actually proved that all the triangles in the right big triangle ABC are correspondingly equal to all the triangles of this small right triangle HCQ. Therefore, those two right triangles are similar to each other according to angle similarity rule. So write it down. Okay, found out that the right big triangle ABC is similar. This is the sign of similar to the right small triangle HCQ according to angle similarity rule. And from the fact the big triangle ABC is similar to the small triangle HCQ, we derive that the following relationship exists between their sides. We derive that side AB in the big right triangle ABC over side HQ in the small right triangle HCQ equals to side BC in the big right triangle ABC over side QC over side edge C in the small right triangle HCQ. Repeat again. We will derive the side AB in the big right triangle ABC over side HQ in the small right triangle HCQ equals to side BC in the big right triangle ABC over side HC in the small right triangle HCQ. AB is 6 over HQ. HQ is B, it is the radius of the big semicircle, and it is equals to BC. BC is 8 according to what is given us the question, over HC. We already found out that HC equals to 4. So if we found out that 6 over B equals to 8 over 4. 8 over 4 is 2. So if we found out that 6 over B equals to 2, here we'll multiply this equation by B and finally get that 6 equals to 2B. Here we divide this equation by 2 and finally get that the radius B of the big semicircle equals to 6 over 2, that is 3. And again, if we found out that the radius B of this big semicircle equals to 3 units in its length, here point Q is the center of the semicircle, point B is the point of the semicircle itself, therefore QB is also the radius of this big semicircle, so QB equals to 3 units in its length. In the next step, we will join points P and N together by straight line. Pn is of course the radius of this small circle, that is the radius that we are looking for in this question. So we will define the radius of this small semicircle as A. So Pn equals to A. So here we can implement rule 1 because we have the radius Pn is equals to A is drawn to point N. That is the point of tendency of tangent AB with this small circle, and whenever you have radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NP. If AB is perpendicular to NP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points P and K together by straight line. PK is of course the radius of this small circle, is equals to A according to our definition. The radius PK is drawn to point K, that is the point of tendency of the tangent AC with this small circle. Whenever our radius that is drawn to the point of tendency, then tangent AC will be perpendicular to the radius KP. If AC is perpendicular to KP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. So, in the next step, I present to you a new rule, and we will implement the new rule in our drawing. The new rule is rule 15. According to rule 15, if from an external point of a circle you will draw two tangents to the circle. Okay. So here we have the external point P. From this common external point P, we drew two tangents to this circle, tangent PA and tangent PB. This way we created angle APB. Then the angle that will be created between the two tangents, the angle that was created between those two tangents PA and BP is angle BPA or APB. This is the angle that was created by drawing two tangents PA and PB towards this circle. And according to rule 15, its angle bisector must pass through the center of the circle. So according to this rule 15, the angle bisector of this angle APB, must pass through point O, that is the center of this circle. So I repeat again, according to rule 15, whenever you draw two tangents to the circle from the common external point P or any other common external point towards the circle, then the angle that will be created between the two tangents, this angle APB. So the angle bisector of angle APB passes through point O, that is the center of this circle. So the angle bisector of this angle APB is OP. Angle bisector OP bisects angle APB into two halves. Each half equals to theta. Okay, so you can say that whenever you draw two tangents from a common external point towards the circle, then the angle bisector of the angle that was created by the two tangents, the angle bisector must pass through point O. You can see here that OP, the angle bisector OP, passes through point O, that is the center of this circle. So we can actually implement rule 15 in our drawing. Why? Because in our drawing, if we focus on this common example point A, from this common example point A, we have two tangents towards this small circle, tangent AN and tangent AK. Therefore, can implement here rule 15. According to rule 15, the angle that was created by the two tangents is this angle, angle A. Again, this is angle A that was created by drawing two tangents from the common point A towards this small circle. So, and according to rule 15, the angle bisector of this angle A must pass through point B, that is the center of this small circle. So, I will draw the angle bisector of this angle A, and know that angle bisector of angle A must pass through point B. So AP is the angle bisector of this angle A, and it passes through point B, that is the center of this small circle. Likewise, so actually, if the side of angle A is 2 theta, then the angle bisector AP or PA bisects angle A into 2 halves. Each half equals 2 theta, of course. This is the first half, and this is the second half. We will continue to focus on this common example point A. From this common example point A, we have two tangents towards the big semicircle. We have tangent AB and tangent AH. Again, we have tangent AB and tangent AH. The angle that was created by drawing the two tangents AB and AH towards this semicircle, the angle is the same angle, angle A. Again, the same angle A was created by drawing two tangents towards the big semicircle. Tangent AB and tangent AH created this angle, the same angle, angle A. And according to rule 15, the angle bisector of the same angle, angle A, passes through point Q, that is the center of the big semicircle. So, I will draw the angle bisector AQ of angle A. So the angle bisector AQ, of course, passes through point Q, that is the center of the big semicircle. So in conclusion, can I know that the angle bisector A passes through point P according to rule 15. The angle bisector of angle A passes through point P according to rule 15, and the angle bisector of the same angle, angle A, passes also through point Q. Repeat again, according to rule 15, the angle bisector of this angle A passes through point P and also passes through point Q. The angle bisector of angle A, of course, also passes through point A. So write it down. The angle bisector of the same angle, angle A, passes through point A also. So in conclusion, we can write down that the angle bisector of angle A passes through point A, P, and Q. Passes through points A, P, and Q. But we also know that the angle bisector of any angle is a straight line. Again, the angle bisector of any angle is a straight line, of course. And therefore, the angle bisector of angle A is located, all the 3 points A, P, and Q are located on the same straight line. So, all the 3 points of the angle bisector of angle A are located on the same straight line. The straight line is actually the angle bisector itself, that is actually a straight line. So all the 3 points A, P, and Q are located on the same straight line, or we can say that line segment APQ is one straight line. So actually this is line segment APQ, and this line segment APQ, this line segment APQ is one straight line. If line segment APQ is a straight line, it means that AQ is also a straight line. So write it down. AQ is a straight line. But if AQ is a straight line, it means that shape AQB is a shape AQB that is a right angle. Again, shape AQB is a right angle. Shape AQB is a right angle. So, in the right angle AQB, this is angle theta, but angle theta belongs also to the right small triangle A and P. So angle theta is a common angle that belongs to both triangles. So we'll focus on the small right triangle A and P. In the small right triangle A and P, this angle equals to theta, this angle equals to 90 degrees, therefore this part missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is equals to 180 degrees. That is the sum of the angles in any triangle. Likewise, if we focus on the right big triangle ABQ, the right big triangle ABQ, this angle equals to theta, this angle equals to 90 degrees, therefore this first missing angle must be equal to 90 degrees minus theta. In the next step, we'll prove that the right big triangle ABQ is similar to this right small triangle A and P. Again, we prove that the right big triangle ABQ is similar to this right small triangle A and P. So why the big right triangle ABQ is similar to this small right triangle A and P? First of all, those two angles they are both equal to 90 degrees, therefore they are equal to each other. So actually this is angle ABQ, and the right big triangle ABQ, and it is equal to this angle, that is actually angle A and P, in the right small triangle A and P. This again, angle ABQ, in the big right triangle ABQ equals to angle A and P, in the right small triangle APN, they are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, that is a common angle that belongs to both triangles. So we can write down that angle theta equals to itself as a common angle that belongs to both triangles. So if we relate to this angle theta as it is belongs to the big right triangle ABQ, it will be defined as angle BAQ. And it equals to itself. So if we relate to angle theta as it belongs to the right small triangle A and P, it will be defined as angle A and P. It will be defined as angle NAP. And this again, this equation means that angle theta equals to itself. We just called to angle theta two different names. And finally, those two angles they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually, this is angle AQB in the right triangle ABQ, and it is equal to this angle, that is actually angle APN in the right triangle ANP. Repeat again. Angle AQB in the big right triangle ABQ equals to angle APN in the right small triangle ANP. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So we actually proved that all the three angles in this big right triangle ABQ are correspondingly equal to all the three angles in this small right triangle ANP. Therefore, those two right triangles are similar to each other according to angle similarity rule. So write it down. We actually found out that the big right triangle ABQ is similar. This is the sign of similar to the right small triangle ANP according to angle similarity rule. And from the fact that the right big triangle ABQ is similar to the right small triangle ANP, we will derive that the following relationship exists between their sides. We will derive that side AB in the right big triangle ABQ over side AN in the small right triangle ANP equals to side BQ in the big right triangle ABQ over side NP in the small right triangle ANP. Repeat again. We derive that side AB in the big right triangle ABQ over side AN in the small right triangle NP equals to side BQ in the big right triangle ABQ over side NP in the small right triangle ANP. AB is 6 over AN. AN is the missing side, so we will leave it as it is. And it is equals to BQ. BQ is 3, it is the radius of the big semicircle. It is equals to 3 units in its length over NP. NP is the radius that we are looking for. In this equation, it is the radius of this small circle, and it is equals to A according to our definition. In conclusion, we should found out that six over AN equals to 3 over A. Here we cross multiply this equation, and we get that 6A equals to 3AN. Here we divide this equation by 3, and finally we get that the missing side AN equals to 6A over 3. 6A over 3 is 2A. So we found out that this missing side AN equals to 2A units in its length. So I write it down. It is given us the question that side AB equals to 6. We just write down, found out that AN equals to 2A, and therefore the missing side NB must be equal to AN. The missing side NB must be equal to AB minus AN. Again, the missing side NB must be equal to AB minus AN. AB is 6, AN is 2A, so total NB equals to 6 minus 2A. So I write it down. In the next step, we do a construction, that is to say, from the center of this whole circle, that is to say, from point P, we will do perpendicular on BQ. Again, from point P, we will do perpendicular on BQ. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and BQ. This point is point Z. By doing this construction, you get the quadrilateral NP-BQ. Inside quadrilateral NP-BQ, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth incident angle. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth incident angle must be equal to 90 degrees in size. So inside quadrilateral NP BZ, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to this quadrilateral NP BZ as a rectangle because it has 4 right angles. So I write it now. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle NP-BZ, side NP must be equal to side BZ. But NPZ, therefore BZ must be also equal to A. Likewise, according to the sub-rule, in the sub-rectangle NP-BZ, side NB must be equal to the opposite side PZ, but NB is 6 minus 2A, therefore PZ must be also equal to 6 minus 2A. What is the length of 9/7 PQ? Actually, in the drawing, we have an external notch between this small circle and this big semicircle. That is to say, they are touching each other externally in this point T. And whenever you have an external notch between two circles, you can implement rule 10. I repeat quickly on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together must pass through their touching point. So, in the drawing we have two circles, and they have an external notch between them at point P. That is to say, they are touching each other externally in this point P. The center of this small circle is here at point M. The center of this big circle is here at point O. And the straight line that connects the centers together is of course the straight line MO. And according to this rule 10, the straight line MO must pass for their touching point, that is P. Again, the straight line MO must pass for their touching point, that is point P. or MPO is 1 straight line. Again, MPO is 1 straight line according to this rule, rule 10. So we can actually implement rule 10 in our drawing. Why? Because in our drawing we have an external arch between this small circle and this big semicircle. That is to say they are touching each other externally in this point T. The center of this small circle is here at point P. The center of this big semicircle is here at point Q. And the straight line that connects the centers together is of course the straight line PQ. And this straight line PQ must pass through point T, that is their touching point. Again, this straight line PQ must pass through point T, that is their touching point. Or PTQ is one straight line. Again, PTQ is one straight line according to rule 10. So, if PTQ is one straight line, it means that PQ is a straight line also. PQ is a straight line. So what is the length of the straight line PQ? Because of the fact that PTQ is a straight line, it means that PQ must be equal to PT plus TQ. Again, PQ equals to PT plus TQ. So I'll write it down. The length of line segment PQ, it is equals to PT plus TQ according to rule 10. So PQ equals to PT. PT is the radius of this small circle. This is the radius that you are looking for in this question, and it is equals to A according to our definition. So PT equals to A plus TQ. TQ is the radius of this big semicircle. We already found out that the radius B of this semicircle equals to 3 units in its length. So in total we actually found out that the length of PQ is A plus 3. Okay, this is 3. So in the next step, I'll copy the right green triangle PZQ. Copy the right green triangle PZQ in a new page, and we'll implement the Pythagoras theorem on this right green triangle PZQ. The hypotenuse PQ equals to A plus 3. Side PZ equals to 6 minus 2A, and side ZQ equals to, what is the length of side ZQ? From the drawing it is very easy to see that ZQ equals to BQ minus BZ. Again, ZQ equals to BQ minus BZ. So ZQ equals to BQ, that is 3, minus BZ, that is A. So in total, ZQ equals to 3 minus A. So actually, this is the green right triangle PZQ that I copied from the original drawing. Here by PT is the version for Pythagoras theorem. According to the Pythagoras theorem, in this right triangle, PZQ, PQ square equals to PZ square plus ZQ square. Again, PQ square equals to PZ square plus ZQ square. So right now, according to the Pythagoras theorem, this right triangle PZQ PQ square, that is the square of the hypotenuse, must be equal to to PZ square plus ZQ square. The hypotenuse PQ is A plus 3, therefore PQ square is A plus 3 square. And it must be equal to PZ square. PZ is 6 minus 2A, therefore PZ square is 6 minus 2A square. Plus ZQ square. ZQ is 3 minus A, therefore ZQ square equals to 3 minus A square. So in conclusion, we should find out that according to the Pythagoras theorem, in the right triangle PZQ, A plus 3 square equals to 6 minus 2A square plus 3 minus A square. We open the brackets on both sides of this equation, and we get that A plus 3 square A plus 3 square equals to A square A plus 3 square equals to A square plus 3 square, that is 9, plus 2 times A times 3, that is 6A, and it is equals to, on the other side of the equation, we have 6 minus 2A square. 6 minus 2A square equals to 6 square, that is 36, plus 2A square, that is 4A square, minus 2 times 6 is minus 12, and minus 12 times 2A is minus 24A. Plus 3 minus A square. 3 minus A square equals to 3 square, that is 9, plus A square, minus 2 times 3 is minus 6, so it is minus 6A. So here we have A square on both sides of the equation, so A square gets cancelled, and we also 9 on both sides of the equation, so 9 also gets cancelled. After cancel those two expressions, in this side of the equation we left only with 6A. On the other side of the equation we have 36 plus 4A square. And here we have minus 24A minus 6A is minus 30A. So we actually found out that 6A equals to 36 plus 4A square minus 30A. Here we subtract 6A from this equation. So in this side of the equation we left with nothing, 0. The other side of the equation we have 36 plus 4a squared, and minus 38 minus 6a is minus 36a. If we found out that 36 plus 4a squared minus 36a equals to 0. Here we divide this equation by 3, and here we divide this equation by 4, of course, and you get that 4a squared over 4 is a squared, minus 36a over 4 is minus 9a, and 36 over 4 is 9, equals to 0. If we found out that a squared minus 9a plus 9 equals to 0, so actually this is a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. Here in this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we will find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared plus 4 times a times c over 2a. Now a specific quadratic equation, that is to say a squared minus 9a plus 9 equals to 0. The variable that we are looking for is a, so x equals to a. The coefficient a equals to 1. The coefficient b equals to minus 9. And finally, the coefficient c equals to 9. The only thing that is left to do is to put the data of our specific quadratic equation in this general formula for x, and we'll find out the value of the values of a, because a equals to x. A is the radius of this small circle, semicircle. A is the radius of this small circle. That is the radius that we are looking for in this question. So we'll do it now. We put the data of this specific quadratic equation in this general formula for x, and we find out the value of the values of a. So x equals to a, therefore a equals to minus b. B is minus 9, therefore minus b is minus 9, that is plus 9, plus minus square root of b squared. B is minus 9, therefore b squared is minus 9 squared, that is 81, minus 4 times a. A is 1, so minus 4 times 1 is minus 4, times c. C is 9, so minus 4 times 9 is minus 36. So inside the equation we left only, inside the root we left only with 81 minus 36 over 2a. A is 1, so 2 times a is 2 times 1, that is 2. If we found out that a, the radius of this small circle, a equals to 9 plus minus, inside the root we have 81 minus 36. 81 minus 36 is 45 divided by 2. So here we have two solutions that are possible for a. The first solution for a is that a equals to 9 plus square root of 45 over 2. This expression is definitely greater than 3, but the radius a of this small circle can never be greater than 3 because of the fact that this small circle is definitely smaller than the big semicircle, and therefore the radius of the small circle must be less than 3 units. Okay, so this solution is the correct solution. You cancel the solution, and we have to leave with the second solution that is possible for A, that is the radius of this small circle. So A, according to the second solution, is equals to 9 minus 4 to 45 over 2. So A equals to 9 minus, it's not the root, we have 45. 45 is 9 times 5 divided by 2. So A equals to 9, and we have here the square root of 9 is 3. So in total, this expression equals to 3 times square root of 5 divided by 2. So the solution of the question is that the radius of this small circle A equals to either 9 plus 3 times square root of 5 over 2 units, or in terms of numbers, it is equals to 1.146 units. And that is the answer to the question. Repeat again, the radius of this small circle A equals to either 9 minus 3 times square root of 5 over 2 units, or in terms of numbers, it is equals to 1.146 units. Okay, so in the next step, I'll summarize the lecture. In this lecture, we found out the radius of this small circle. So in the drawing, we have the right triangle ABC. Side AB of the right triangle ABC equals to 6 units in its length. Side BC equals to 8 units in its length. Angle ABC is the right angle. Inside this right triangle ABC, we have this small circle, and we also have this big semicircle. Touch each other at this point. And our mission is to find out the radius of this small circle. So in the first step, we implemented the Pythagoras theorem on this right triangle, triangle ABC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So that is to say, in this right triangle ABC, it means that AC square equals to AB square plus BC square. Repeat again. According to the Pythagoras theorem, in the right triangle ABC, AC square equals to AB square plus BC square. So AC square equals to AB square. AB is 6, therefore AB square is 6 squared, that is 36, plus BC square. BC is 8, therefore BC square is 8 squared, that is 64. So in total, AC square equals to 36 plus 64, that is 100. So AC square equals to 100. And to go out of this equation, find out that the missing hypotenuse AC is equals to 10 units in its length. The next step, I implemented rule 2 in our drawing. If we focus on this common point, point A, from this common point, point A, we have two tangents to the big semicircle, tangent AB and tangent AH. And according to rule 2, they are equal to each other. This is to say AB equals to AH. Again, AB equals to AH. But according to what is given in the question, AB equals to 6. So we can write here that AB equals to 6. And from this equation, 6 equals to AB equals to AG, we will derive that AH also equals to, again, from this equation, 6 equals to AB equals to AH, we will derive that AH also equals to 6 units in its length. This is line segment AH is equals to 6 units in its length. And therefore, the distance side HC must be equal to AC minus the distance side HC must be equal to AC minus AH. So the distance side HC equals to AC, that is 10, minus AH, that is 6. So in total, HC equals to 10 minus 6, that is 4. Okay, in the next step, we define the center of this small circle. This point is point P. We define the center of this big semicircle. This point is point Q. We join points Q and H together by straight line. QH is the radius of this semicircle. We define the radius of this semicircle as B. Here we implemented rule 1. We have the radius QH that is on to point H, that is the point of tendency of tangent AC with this big semicircle. Whenever you have a radius that is on to the point of tendency, then tangent AC will be perpendicular to the radius HQ. If AC is perpendicular to HQ, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. So actually, this is angle C. This angle C, it is a common angle that belongs to both angles. It belongs to the big right angle ABC, and angle C also belongs to the right angle HQC. So we define the size of this angle C is alpha. So in the right angle HQC, this angle equals to alpha, this angle equals to 90 degrees, therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in the triangle. Okay, likewise, if we focus on the big right angle ABC, the big right angle ABC, this angle equals to alpha, this angle equals to 90 degrees, therefore this first missing angle must be equal to 90 degrees minus alpha. In the next step, we prove that the big right angle ABC is similar to this small right angle HQC. So why those two right angles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha, this is a common angle that belongs to both angles, so we can write down that angle alpha equals to itself. It's a common angle that belongs to both angles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually proved that all the triangles in the big right angle ABC are correspondingly equal to all the triangles of this right small triangle HQC. And again, we found out that all the triangles of the big right triangle ABC are correspondingly equal to all the triangles of this right triangle HQC. And therefore, the big triangle ABC is similar to the small right triangle HQC according to angle similarity rule. Okay, again, the big right triangle ABC is similar, this is the side of similar to the right triangle HCQ according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AB in the big right triangle ABC or side HQ in the small right triangle HCQ equals to side BC in the big right triangle ABC or side SC in the small right triangle HCQ. Repeat again. We derive that side AB in the big right triangle ABC or side HQ in the small right triangle HCQ equals to side BC in the big right triangle ABC or side HC in the small right triangle HCQ. AB6, HQ is B, it is the radius of the semicircle, BC is 8, and HC is 4. So if we're going to find out that 6 over 4 equals to 8 over 4, 8 over 4 is 2. So total we found out that 6 over B equals to 2, we multiply this equation by B, and finally found out that 6 equals to 2B, here we divided this equation by 2, and finally found out that B equals to 6 over 2, that is 3. So the radius B of this big semicircle equals to 3 units in its length. Okay. In the next step, I presented to you a new rule and implemented the new rule in our drawing. Actually, the new rule is rule 15. according to rule 15, if from an external point of a circle you will draw two tangents to that circle. Here we have the common start point P. From this common start point P, we draw two tangents to this circle, tangent PA and tangent PB. In this way, we get this angle. This is the angle between the two tangents. So, if from an example point of a circle you draw two tangents to the circle, then the angle that will be created between the two tangents, that is to say angle APB, the angle bisector of this angle APB must pass through point O, that is the center of this circle. Again, the angle bisector that is created by two tangents is angle APB. The angle bisector of this angle must pass through point O, that is the center of this circle. So I can actually implement rule 15 in our drawing. Why? Because in our drawing, if you focus on this common point A, on this common point A, we have two tangents to this small circle, tangent AN and tangent AK. And those two tangents create angle A between them. Again, those two tangents AN and AK create angle A between them. And according to rule 15, the angle bisector of this angle A must pass through point P, that is the center of this small circle. Again, the angle bisector of this angle A must pass through point P, that is the center of this small circle. Okay, again, actually, according to rule 15, the angle bisector of angle A passes through point P according to rule 15. Likewise, we will continue to focus on this common start point A. For this common start point A, we have two tangents to this big semicircle, tangent AB and tangent AH. And by drawing the two tangents AB and AH, we actually created the same angle A. Therefore, we can implement here rule 15. According to rule 15, the angle bisector of this angle A must pass through point Q, that is the center of this big semicircle. Again, the angle bisector of this angle A must pass through point Q, that is the center of this big semicircle. So, again, I should found out that the angle bisector of angle A, the angle bisector of angle A passes from point Q. And it is trivial that the angle bisector of angle A must also pass from point A, of course. So here I wrote it down that the angle bisector of angle A passes also from point A. So conclusion, we found out that the angle bisector of angle A passes from points A, P and Q. The angle bisector of this angle A passes from point A, P and Q. And because of the fact that the angle bisector of any angle is a straight line, it means that the 3 points A and P and Q are located on the same straight line, that is the straight line that is the angle bisector of this angle A. Because angle bisector is a straight line, and therefore the 3 points are located on the same straight line, that is the angle bisector of angle A. And again, the angle bisector of angle A passes from points A, P and Q, and all the 3 points of the angle bisector of angle A are located on the same straight line. That is the angle bisector itself of angle A. Or again, all the 3 points A and P and Q are located on the same straight line. Or we can say also that line segment APQ is one straight line. Again, line segment APQ is one straight line. If line segment APQ is one straight line, it means that AQ also is a straight line. So AQ is a straight line, and therefore the shape AQB, the shape AQB is a right angle. Because of the fact that AQ is a straight line, it means that shape AQB is a right angle. Again, shape AQB is a right angle. So if you focus on this right angle AQB, this is angle theta, that is a common angle that belongs to both angles. Angle theta belongs to the big right angle ABQ, and angle theta also belongs to this small right angle ANP. Okay, so if you focus on this right small triangle ANP, this angle equals to theta, this angle equals to 90 degrees, therefore this missing, this further angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, in the right triangle ABQ, this angle equals to theta, this angle equals to 90 degrees, therefore this further angle must be equal to 90 degrees minus theta according to the same rule that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we proved that the right big triangle ABQ is similar to this small right triangle ANP. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, that is a common angle that belongs to both angles, so we can write down that angle theta equals to itself as a common angle that belongs to both angles. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So we should prove that all the angles of the right triangle ABQ are correspondingly equal to all the angles of this right small triangle ANP. Therefore, those two right triangles are similar to each other according to angle similarity rule. So repeat again, we actually found out that the right big triangle ABQ is similar, this is the sign of similar, to the right small triangle ANP according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AB, the big right triangle ABQ, over side AN in the small right triangle ANP, equals to side BQ in the big right triangle ABQ over side NP in the small right triangle NP. Repeat again. We will derive that side AB, the big right triangle ABQ over side AN in the small right triangle NP equals to side BQ in the big right triangle ABQ over side NP in the small right triangle NP. AB6, AN is the missing side, so we leave it as it is. BQ is the radius of the semicircle that is free. And finally, NP equals to A, it is the radius that we are looking for. It is the radius of this small circle, that is the radius that we are looking for in this question. So in conclusion, I actually found out that 6 over AN equals to 3 over A. Here we cross multiply this equation and finally found out that 6A equals to 3AN. Again, 6A equals to 3N. Here we divided this equation by 3 and finally found out that the missing side AN equals to 6A over 3, that is 2A. Again, this is the missing side AN, that is equals to 2 units in its length. We know that AB equals to 6, AN equals to 2A, and therefore the missing line segment NB must be equal to AB minus AN. Again, NB equals to AB, that is 6, minus AN, that is 2A. So in total, NB equals to 6 minus 2A. In the next step, from the center of this small circle, that is to say from point P, we draw perpendicular on BQ. Again, from point P, we draw perpendicular on BQ. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and BQ. This point is point Z. By doing this construction, we get the quadrilateral NPBZ. Quadrilateral NPBZ has 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4th missing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4th missing angle must be equal to 90 degrees in its size. So inside quadrilateral NPBQ we have 4 right angles. And therefore, according to rule 5, any quadrilateral that has 4 right angles must meet this rectangle if it has a square. So we relate to this quadrilateral NPBZ as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So an rectangle NPBZ, side NP must be equal to the opposite side BZ. But NPZ, therefore BZ must be also equal to A. According to the same rule in the same rectangle NPBZ, side NB must be equal to the opposite side PZ. But NB is 6 minus 2A, therefore PZ must be also equal to 6 minus 2A. What is the length of the missing line 7 QZ? From the drawing it is very easy to see that QZ equals to BQ minus BZ. Then again, QZ equals to BQ minus BZ. BQ is 3, BZ is A. So in total, QZ equals to 3 minus A. What is the length of PQ? Actually, we have an external notch between this small circle and this big semicircle. That is to say they are touching each other externally at point T. Okay, and whenever you have an external notch between two circles or semicircles, you can implement rule 10. I repeat quickly on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together must pass through their touching point. So in the drawing we have two circles and they have an external notch between them at point P. That is to say they touch each other externally at point P. The center of this small circle is at point M. The center of this big circle is at point O. And the straight line that connects the centers together is the straight line MO, of course. And this straight line MO must pass through point P, that is their touching point. Again, the straight line MO must pass through point P, that is their touching point. Or MPO is one side line. MPO is one side line. So we can actually implement all 10 in our drawing. Why? Because in our drawing, we have an external notch between this small circle and this big semicircle. That is to say, they are touching each other externally at point T. Therefore, we can implement here rule 10. According to rule 10, the center of this small circle is at point P. The center of this big semicircle is at point Q. And the straight line that connects the centers together is, of course, the straight line PQ. And this straight line PQ must pass through point T, that is their touching point. Again, the straight line PQ must pass through point T, that is their touching point. Or PTQ is one side line. Again, PTQ is one side line according to rule 10. If PTQ is one side line, it means that PQ is a straight line. And because of the fact that PTQ is one side line, it means that PT, it means that the length of PQ is PT plus TQ. Again, PQ plus 2 PT plus TQ because of the fact that PTQ is one side line according to rule 10. So PQ equals to PT. PT is A, this is the radius that we are looking for in this question, plus TQ. TQ is 3. So in total, PQ equals to A plus 3. In conclusion, we found out that the hypotenuse of this right green triangle PZQ, the hypotenuse PQ is A plus 3. In the next step, I copied this right green triangle in an Olympiad and implemented the Pythagoras theorem of this right green triangle PZQ. Actually, this is the right green triangle PZQ that I copied from the original drawing. According to the Pythagoras theorem, this right triangle PZQ, PQ square equals to PZ square plus ZQ square. Again, PQ square equals to PZ square plus ZQ square. PQ is A plus 3, therefore PQ square is A plus 3 square equals to PZ square. PZ is 6 minus 2A, therefore PZ square is 6 minus 2A square plus ZQ square. ZQ is 3 minus A, therefore ZQ square is 3 minus A square. So in conclusion, I shall find out that A plus 3 square equals to 6 minus 2A square plus A plus 3 minus A square. We open the brackets on both sides of this equation and we have found out that A plus 3 square equals to A square plus 3 square, that is 9, plus 2 times A times 3, that is 6A, and it is equal. On the other side of the equation we have 6 minus 2a squared. 6 minus 2a squared equals to 6 squared, that is 36, plus 2a squared, that is 4a squared, minus 2 times 6, that is minus 12, times 2a, minus 12 times 2a is minus 24a, plus 3 minus a squared. 3 minus a squared equals to 3 squared, that is 9, plus a squared, minus 2 times 3 times a, that is minus 6a. So here we have a squared on both sides of the equation, so a squared will get cancelled. And we also 9 on both sides of the equation, so 9 also will get cancelled. After we cancel those two expressions, in this side of the equation we left only with 6a. In the other side of the equation we have 36 plus 4a squared, minus, here we have minus 24a minus 6a is minus 38. So we actually found out that 6a equals to 36 plus 4a squared minus 38. Here we subtracted 6a from the equation and finally found out actually in this side of the equation we left with nothing, 0. In the other side of the equation we have 36 plus 4a squared, and minus 38 minus 6a is minus 36a. So we actually found out that 0 equals to 36 plus 4a squared minus 36a. Here we divided this equation by 4 and finally found out that 4a squared over 4 is a squared, minus 36a over 4 is minus 9a, 36 over 4 is 9. So in conclusion we found out that a squared minus 9a plus 9 equals to 0. So this is a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula: x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, that is to say a squared minus 9a plus 9 equals to 0, the variable that we are looking for is a, therefore x equals to a, the coefficient a equals to 1, the coefficient b equals to minus 9, and finally the coefficient c equals to 9. So the only thing that is left to do is to put the data inside this formula for x, and we find out the value of the values of a, because x equals to a. A is the radius of this small circle, that is the radius that we are looking for in this question. So we actually put the data of our specific quadratic equation in this general formula, and found out that x is a equals to minus b. B is minus 9, therefore minus b is minus 9, that is plus 9, plus minus b squared. B is minus 9, therefore b squared is minus 9 squared, that is 81, minus 4 times a. A is 1, so minus 4 times 1 is minus 4 times c, that is 9. So minus 4 times 9 is minus 36 over 2a. A is 1, so 2a is 2 times 1, that is 2. So a equals to 9 plus minus square root of 81 minus 46 over 2. So 81 minus 46 is 45. So inside the root we left only with 45. And actually found out that the radius a of this small circle equals to 9 plus minus square root of 45 over 2. So here we will have two solutions that are possible for a. The first solution for a is that a equals to 9 plus square root of 45 over 2. But this expression is definitely greater than 3. But the radius of this small circle a can never be greater than 3 because of the fact that the radius of this big semicircle equals to 3. And you can see from the domain that this small circle is definitely smaller than the big semicircle, therefore its radius must be also smaller than 3. This is the radius of the big semicircle. So we cancel this solution because the radius a can never be greater than 3. And we left only with the second solution that is possible for a. The second solution for a is that a equals to 9 minus square root of 45 over 2. 45 is 9 times 5, so we substitute 45 by 9 times 5, and actually found out that a equals to 9 minus square root of 9 times 5 over 2. The square root of 9 is 3, so in total a equals to 9, and here we have the square root of 9 is 3, so in total this expression equals to 3 times square root of 5 over 2. So actually found out that the radius of this small circle, the radius a equals to either 9 or 3 times square root of 5 over 2 units. In its name, or in terms of numbers, the radius a of this small circle equals to 1.146 units. Okay, thank you very much.